What if the biggest energy story right now is not a finished power plant, but a pattern? Fusion has been almost here for decades. That is the joke. But in the last few years, something real changed. Different machines, built for different physics problems, started crossing lines that used to be out of reach. At the National Ignition Facility in California, lasers hit a tiny fuel capsule for a few billionths of a second. In April 2025, that target absorbed 2.08 megajoules of laser energy and produced 8.6 megajoules of fusion energy. That is not electricity from the wall. It is not a power station. But at the target, it was more than 4 times the laser energy delivered to it. That matters because ignition is no longer a single lucky headline from 2022. NIF has repeated it, improved it, and shown that tiny details such as capsule quality can turn into huge changes in fusion yield. Now switch from lasers to magnetic confinement. A tokamak, or stellarator, is trying to hold a plasma hotter than the core of the sun without letting it touch the wall. The challenge is not just making it hot. The challenge is keeping it stable, clean, and controllable for power plant timescales. China's East Tokamak reported a 1,066-second high-confinement plasma in January 2025. That is almost 18 minutes. A few weeks later, France's West Tokamak pushed a plasma to 1,337 seconds, more than 22 minutes. West was not claiming massive fusion power. It was proving something more practical. Long pulses, active cooling, tungsten-facing components, and control systems can survive a serious endurance test. Then there is Wendelstein 7X in Germany. It is not a tokamak. It is a stellarator, a twisted magnetic machine designed for steady operation. In May 2025, W7X set a long-duration record for the triple product, a key measure combining density, temperature, and confinement. For short bursts, tokamaks still lead. But for long pulses, the stellarator case is becoming harder to ignore. And before it shut down, JET in the United Kingdom gave fusion one more crucial data point. In its final deuterium-tritium campaign, European researchers released 69.26 megajoules of fusion heat over 6 seconds. JET did not run continuously. It did not make net electricity, but it did operate with the fuel mix future reactors actually need. So is this the breakthrough? Scientifically, yes, in pieces. NIF shows ignition and target gain. JET showed real deuterium-tritium heat. East and West show endurance. Wendelstein 7X shows that stellarators can compete on long pulse confinement. Together, these are not one finished machine. They are a map of the hard parts becoming less mysterious. But here is the reality check. A power plant has to do all of this at once. It must heat plasma efficiently, confine it for long periods, breed or supply tritium, survive neutron damage, remove heat, run many times per day or continuously, and convert thermal energy into electricity at a price that can compete on the grid. Target gain is not wall plug gain. Plasma gain is not whole plant gain. A record plasma pulse is not commercial power. The difference between a physics milestone and an energy product is engineering, materials, maintenance, regulation, and cost. ITER shows the scale of that gap. Its mission is to demonstrate integrated scale fusion operation, with a goal of 500 megawatts of thermal fusion power from 50 megawatts of heating power to the plasma. But ITER has also had to update its schedule because first-of-a-kind components, quality issues, and assembly complexity were harder than expected. That is not a reason to dismiss fusion. It is the reason the recent records matter. They are attacking the bottlenecks one by one. The honest headline is not "free energy tomorrow." The honest headline is more interesting. Fusion is moving from proof-of-principle moments into repeatability, duration, materials, and systems integration. If those curves keep improving, the next breakthrough will not be one spectacular flash. It will be a machine that can run, recover, repeat, and pay for itself. That is the line fusion still has to cross. And for the first time in a long time, the path to that line looks less like science fiction and more like engineering.